Thank you to everyone who has joined us today. We have more than 600 people registered, which is a new record. Really happy to see so many people in the AI community in the UK and elsewhere interested in data-related aspects. We'll start in a second, but before I do, and while everyone is joining, let me just go through a few housekeeping topics. This webinar should be recorded. My colleagues in the control room at the ODI will probably start the recording soon. We will share the recording on social media and on various channels, and we will post the recording on the event page and our YouTube channel as well. And we'll also use quotes and snippets from the recording in future ODI communications. As always, if you want to ask a question, add it to the Q&A section throughout the talk, and we'll get to it. And if you have any other questions, the ODI team is there to help you. So just use the chat. This is the 5th webinar in the series. Initially, we were planning to do 6 webinars. We didn't really know how much appetite there is there in the community for this sort of topics, but we've been overwhelmed by the response. So we have been extending the series. So I'm happy to announce as well that we will be continuing in the new year. But here on the slide, you have a QR code that will get you to the landing page of the webinar series, where you can see recordings of the webinars we had so far. And we featured a whole range of topics in this data-centric AI universe, starting with a talk on safety data sets and their cultural diversity, and then moving on into legal and technical challenges around data scraping, talking about data workers' rights, and then talking about one of the most important AI data commons as part of our data-centric AI program, which many of you are already familiar with. Well, today is a special day. Because we are welcoming Sir Nigel Shadbolt, Professor Sir Nigel Shadbolt, our co-founder here at the ODI and executive chair. I'm going to read Nigel's CV.
Oh, no.
Yes, I'm going to do this. In fact, I'm just going to pick on a few of his achievements. Besides being one of the most well-known AI scientists in the UK and one of the originators of the field of web science, Nigel is a principal of Jesus College, Oxford, and a professor of computer science at Oxford as well as a visiting professor of AI at the University of Southampton, something I did not know. Some of you may remember that he and our other co-founder, Sir Tim Berners-Lee, were appointed by the Prime Minister in 2009 as information advisors to transform how public sector information was published and used across government in the UK and elsewhere. And one of the achievements of these roles was data.gov.uk, which I personally think it was the first open government data portal. Some might dispute that, especially in the US, but it was the first notable open government data portal. And that was the beginning of a journey for the ODI. As well. In 2010, Nigel joined the UK government's Public Sector Transparency Board, where he oversaw the open data releases across the public sector. He's a fellow of the Royal Society, Royal Academy of Engineering, and a fellow and former president of the British Computer Society. And with that, I will hand over to Nigel, who's going to tell us about his views and work in data infrastructure for AI. Welcome, Nigel.
Thank you so much. I am going to share my screen, if that is okay. So let me just do that, and hopefully I will be.
Yep.
You'll be able to see that. Okay. Yep. Is that all right? Everybody can see that. Yep. Okay. Let me just. So there on the screen you can see the a very notable piece actually appeared in the FT. It's a lovely collage of Demis Hassabis and with Jeff Hinton there, and John Jumper and John Hopfield, who were awarded the Nobel Prizes in physics and chemistry. And I think that was notable just because it underscored how extraordinarily influential AI had become, not just in general conversation, not just within governmental circles or business circles, but actually within scientific circles themselves. And indeed, one of the societies that I'm proud to be a member of, the Royal Society, has just published a very interesting report on science in the age of AI, which I can commend, available on their website, which talks about the real breakthroughs we're seeing because of the application of AI to science. I wanted to say something initially, if about a particular view that I bring to AI. It's not a particular view. It's an important thing to emphasize, which is that AI isn't just machine learning. It's a very large collection of methods and techniques, and at various times, some of these techniques come to the fore. At the moment, much of the excitement around generative AI is based on a particular architecture, a deep learning architecture known as transformer architectures. I'll talk a little bit about this, but it's fair to say that AI is an expanding set of tools and methods, and indeed we're seeing increasing evidence that the most capable AI systems are in fact federations of particular methods and techniques. There isn't one method that rules them all, so to say, but some methods that have a long history in AI. And AI has been around, at least as a distinct term of art, since 1956. For the last 70 odd years, people have been developing methods, and as compute power has increased, as data has become more available, we've seen really remarkable steps. So let me start off with perhaps a traditional view of what AI was. When I was beginning the field in the late 70s, we were busy building what were called decision support systems or expert systems. And indeed, our way of thinking about the way we represented the world of problem solving and data was using explicit structured representations. Indeed, you can see that little example. One approach, which we refer to as symbolic, actually breaks the world, an expert's knowledge, into particular sets of rules and particular descriptions of the objects of interest for that expert. So somebody working in a simple medical application might have a set of heuristic rules that tell them how to imagine whether or not an individual has got a particular infection. And infections come in all sorts of types and subtypes. As you can see, literally read those rules off of the page, more or less. And the effort was to articulate the knowledge an expert had and represent it in these rules and structured objects. So this particular approach, focused very much on the manipulation of these explicit symbols. And it's done hugely well, I should say. The idea that somehow this strand of AI is now defunct, we're seeing it represented in many of the modern systems as well, as I'll mention, but many accomplishments under the belt, not least in automated theorem proving, mathematics. There's a few examples of the sorts of use to which these tools have been put. But a second approach had a very different approach to this, so-called subsymbolic AI. And subsymbolic in the sense you will not find in these systems explicit rules that tell you how to determine whether a particular lesion you're looking at on your skin is malignant or not. Here we see a pictorial representation of a multi-layer deep neural network that is able to take images of it's a cartoon representation, more complicated than this, but many layers of nodes connected via weights. So taking an inspiration from how actual neural biological networks are configured. And the trick in these representations is to adjust the weights between the various nodes, layer on layer. And if you encode across the input layer that you can see on that representation in the top of that description, the input layer, a representation, say, of the pixels or the structures representing a medical image, then as you learn after representation of many examples to categorize outputs by adjusting weights on whether or not a categorization has been successful. And the example I chose there was a system which was written up in Nature just in 2017 and had quite an impact because it was a system that was performing to the level of expert dermatologists, able to determine between benign and not benign skin lesions. But the fact about these representations is there are no explicit predefined rules or symbols. The whole system works by adjusting weights to make effective predictions and classifications. So learning in this case requires adjusting connections between these artificial neurons. And over the subsequent decades, and the last decade or so, has seen an explosion of different types of neural network. And there's just a few examples there. You'll often hear these talked about in the literature, from convolutional neural networks through to transformers, each of which have particular strengths in terms of how they reason over data and how they're able to optimally find satisfactory outcomes. With increasing amounts of architecture, increasing amounts of innovation, increasing compute power, and increasing data, which we'll come on to, this has really opened up an explosion that we've now come to see the culmination with some of these generative AI systems. So this is an early version of ChatGPT, actually able to write quite successful answers to Oxford entrance exams, in fact, or lines of code in Prolog. And the transformer architecture here is illustrated just, again, schematically in terms of the fact that these systems are trained on huge amounts of data. In this case, the transformer architectures, so a system like ChatGPT, the large language model, its entire purpose is to predict the next most likely token in a string, an output string. It does that by having been trained on huge swathes of data taken from the web to encode the probabilities of one word succeeding another in a particular context. The context is a very wide range of previous words. So the internal representations of these systems are huge collections, very large representations in a very high dimensional representation space of the likelihood of words following one another. And which is why that some people have talked about these systems as almost like the ultimate text completion system. And it is really an explosion of models. So here you can see on the left, I've taken a couple of very nice images that represent this explosion of models. Just in a world of one style of machine learning, the transformer models, essentially, we have seen this explosion of models. So on the right, on the left, various versions of models from OpenAI, from Google and elsewhere, Anthropic. On the right is a nice depiction of just one model, actually an open source model that Facebook released. Part of it was released openly, another part was leaked. It turned out that the whole thing was then released, and it's been a particularly interesting model set because it's had lots of innovation, because the weights, the models, the code are all open. And there is a contest at the moment about how big models need to be, whether they should be open and closed, and what data they're trained on. So I want to come on to those issues now. The striking fact about these models is that they are extraordinarily hungry of data. hungry for data. The largest models now trained on extraordinary amounts of input. There is a genuine worry that we might literally run out of human-generated content on the web. The text, the books, the Wikipedia articles, the social media scrapes, all of these ingested by these models. At what point do we think we're going to run out? And anticipating that, people have begun to look at the whole issue of whether or not you need to generate synthetic data. The systems themselves can generate output, so why wouldn't we use that? Data is the feedstock of these systems, so the quality and nature of this data becomes very consequential. And that's what I want to kind of focus on in the rest of what I'm going to say, my remarks, and then in discussion with Eleanor. Well, one thing to note when systems are trained on their own data is strange things start to happen. This has been variously termed MAD, model autophagy disorder, based on the idea of a self-consuming loop. You get a deterioration of content if you strictly feed a model, a conversational model, with its output, and then the next generation with its own output. Generation after generation, you can begin to see real deterioration. You see a similar thing in the artifacts produced in automatic image generation. In a sense, of course, the models have no sense of what the coherence of actual lived human experience and text is. They're relying on the humans to have written that. And if they begin to introduce small, likely, but nevertheless fallacious next word predictions, that can gradually stack up. And in a paper that was written by colleagues, some of them here in Oxford, called The Curse of Recursion, by Shamalyov, we actually see just how degenerate that can be. You can see in the top right there, outputs that become increasingly incoherent. Referred to as model collapse, people have become very concerned to work out what are the conditions under which models trained on their own content might begin to suffer. How do we ensure the quality and nature of the data being used? Okay, sorry, I didn't mean to do that. I've just gone to, let me go to, there we go. Another aspect of the use of synthetic data or model-generated data is that because of the nature of these systems, that they predict the next most likely outcome, distributions tend to become clipped. They regress to the mean. What this means is that unlikely events are increasingly phased out, and likely events become even more represented. There's a regression to the mean. So this is another aspect to which we need to pay attention. Suffice it to say, this isn't to say that this renders these models unusable. In fact, there's a lot of work around synthetic data to ensure that we can trust and detect these kinds of effects. But it does speak to the fact that at the very least, we would do well to know when our models are being trained on synthetic or by data from which particular systems, human systems, scientific instruments generating this, or machine learning systems themselves. Just to say, however, that the use of well-organized data has been one of the breakthrough achievements and accomplishments for the work, for example, in AlphaFold, the work that Demis Hassabis was and Jumper awarded the Nobel Prize for, was actually, if you look at the architecture for these systems, you'll notice on the left-hand side in diagram A there, you'll see a whole set of references to sequence databases and protein databases that were used in the training of the AlphaFold system. What effective scientific AI accomplishments are relying on is very well curated, very well managed data as the feedstock. It's a crucial, important distinction to make. AlphaFold itself was trained to work out how to conform or to predict the actual way in which proteins would fold, which in turn determines some of their properties and indeed how we might design molecules to interact with them. So this becomes a super important capability, and the quality of data assets that were available to people, to the researchers at DeepMind to do this was a crucial feature. And moreover, that this data was available as open data so that the performance of these systems could be evaluated and tested, and indeed ultimately the models, the weights and the data released for wider use. Which brings us to the importance of data in all of this. This is a slide that the ODI originated, which was to remind ourselves that data comes in all sorts of species and varieties, from closed data through to fully open, through data that we choose to share in particular ways. It comes from in all sorts of sizes and shapes, from small to medium to so-called big data. It may have originated as personal data, commercial data, or government data. And these dimensions to the data universe are important as we understand what might be out there, what we can use to train, and how we can attest to the provenance of the data. So the thing we always emphasize at the ODI is the foundational role of open data. I referenced it in that example of scientific discovery, the importance of people being aware of the data that's available, of certain sort of data literacy, and also capable of reflecting on its quality, to actually regard data as an actual infrastructure, not used metaphorically, but actually as an infrastructure. And I'll talk about that briefly, that we would want to assure the data, that would want to test, evaluate, possibly even certify some of the data that's being used, that we might choose to build institutions to curate and steward that data so that we have confidence in it, in its quality into the future, or as new data is generated, bringing those into data institutions. And finally, the importance of ethics. Are we doing the right thing by the data, with the data? Is it appropriately governed? And in some cases, is it subject to actual regulation? So, back in the day when Tim and I were first launching our ideas around how to build open data portals, we were advancing this concept of an idea from work that we had done together in the semantic web of so-called linked data. Very high quality data that actually is linked from one data element to another using a particular set of standards to represent the data. We're still glad to see that there are reference examples to that in the open data space. We got an ambition back then that this way of building a data infrastructure could become very widespread in the public sector. This is work in progress. I won't begin to promise that this has happened everywhere, but because the data question is so important, it is something I believe that we should be revisiting, to think about how we ensure that a data infrastructure can work. This is some work that I did during with colleagues in looking back over the pandemic. Our experience in how we use data during COVID was particularly, I think, helpful for us to understand what well-stewarded data might mean in the future. This actually comes from a paper that has appeared in a special issue of a journal called Epidemics, which is a leading journal in the field of epidemiology, where we imagine the lessons from the pandemic and what the challenges of data might be in future pandemics. What we were recommending was fundamentally an idea that is known in scientific data sharing circles as FAIR, the FAIR principles, that data should be findable, accessible, interoperable, and reusable. It was a surprising fact to us that we discovered that in many areas of clinical and medical scientific practice, that wasn't the case. We had to work very hard to find many of the data assets that we needed. We had to change the conditions of use of some data as we went forward. And indeed, notably, we were able to convince private commercial entities who collected data to make some of that data available for the wider public good. the whole idea of how we set up an ecosystem for data in which policies, data institutions, data policies, data skills, and data platforms, in a certain sense, cooperate together. An idealized version of this is in our paper. We understand that there are many challenges in all of this, but if something as existential as the pandemic can teach us lessons, we think they're well worth taking. When I talk about data as infrastructure, when we talk about it at the ODI, what are we actually requiring of our data? And if we take our model from infrastructures that are actually physically built, that we understand, whether it's the electric grid or the road system or railways, we have expectations around their reliability and usability, that an infrastructure should be reliable. It should be capable of being repeated. There isn't massive variation in the practice of generating data. It should be efficient. There's a trade-off between efficiency, the amount of effort one has to put in to generate it, but it should be scalable, ideally transparent, repurposable, revisable, that it should always have associated with it considerable amounts of metadata that describe how it originated, its terms of use, for example, its provenance, its quality, the conditions under which it was collected. There are entire schemas and additional guidelines about how data can describe data, the metadata, the self-describing data that we're after. And we're also keen that when we build these infrastructures, we find the right level of abstraction, how we can find a level at which services, users, and indeed algorithms can use the data effectively. And in the world of open data, I've given a few reference examples there, which I think illustrate this very well, from the Ordnance Survey, from Transport for London, and indeed from a drug data infrastructure format developed by schema.org. And the standards are one thing, the conditions to which we hold them are one thing, but this isn't just about technical infrastructure, it's about institutional infrastructure as well. We can think of the institutions that we might need to innovate and develop to help look after this data. I think many of us think that in the general case, an awful lot of the rush to generative AI has made very large scale integration and harvesting of data almost a contested point. There are all sorts of questions around IP protection, whether originators have been fully acknowledged and recognized. In the case of the AlphaFold example, of course, those databases were curated, were available for open use. There was no problem with the appropriation of those for the task at hand. But when we look at building our systems, we need to ask, are the institutions that might hold this data or currently hold the data, is this something we need to think about helping support, structure, and develop? And indeed, one of the functions at the ODI is to help both sectors, organizations, and in some cases we do it ourselves, establish data trusts for particular purposes. Behind all of this is a requirement for literacy, that we, when we really understand exploiting data at scale in pressing circumstances, and this again is example taken from the paper I referenced earlier, which was an analysis of the important functions that you need to get data to the point of being used fairly, equitably, and safely. It isn't just about the experts who know where the data assets lay. It's about the roles that people have in licensing the data, people who understand the detailed nuances in the qualities of the data, data analysts and curators who can actually get under the skin of how the data can be purposed and repurposed. And there's an awful lot we can learn, I think, from experiences in the past as we think about how data needs to be stewarded in an era of generative AI. So I'm going to finish with that and turn over to a discussion with Ona.
Excellent. Thank you very much. So I'm going to run through my little Proust questionnaire, data-centric AI edition. So we talked about data-centric AI at the ODI. So I'm asking everyone, including our founders, what data-centric AI is for them. And you've already spoken about symbolic and sub-symbolic AI. So what does it mean to you?
It means recognizing that virtually every technique in the AI canon and method requires data. In some cases, some of the methods require much less data than others, interestingly enough, but they all are essentially, it's the other face of the coin. The algorithm on the one hand, and the data that is being used to inform the algorithm. So in some cases, in the rule-based reasoning, it would have been the initial data fed into the system in terms of trying to determine whether a particular outcome held or not. In the case of a neural network, it is very much concerned initially with the initial training data, but it may well then relate to subsequent use of data to refine and tune the model as well, or indeed to benchmark it. So benchmarking is itself a type of data that is used in the surface of understanding and evaluating. So it's to remind people that without the data, the systems can't be trained, without the data, they can't be tuned, and without the data, they can't be evaluated. And that pretty well holds across large swathes of current AI. And even where there aren't large training sets, the question of data origination is still an important one.
Thank you. Thank you for that. So do you think data has become more or less important since 2 years ago when ChatGPT came to light?
Oh, I think it's become more important. I mean, partly it's a resource that we are becoming ever more aware is central. Of course it is. Do we have enough high quality data? As the large models get larger, where will that data come from, given that huge amounts of what is immediately available has been already ingested? So where will that come from? People say, well, there's lots of data still to be had in private sources, in proprietary data, and of course, then the argument is about the terms and conditions under which that data could be included, how that will be used in training. So that's become an important dimension of discussion. But so has the issue about what if the data, in some sense, is inherently problematic? How would we know if some key data set has been poisoned or manipulated, or in some sense has become unstable because of repeated use by AI generating systems? So those are just two dimensions. Another dimension would be questions around the actual extent to which particular data assets seem to be super important to particular aspects of the system's performance. So there's various work you can do here, so-called ablation studies, where you remove parts of the network that seem to be relating to a particular area of expertise, or you do experiments where you remove a data asset and see whether performance has been affected or not. And one of the interesting questions here is that what people might have thought was the important data for a particular task, if you remove some of that data, it may or may not have a big effect. I remember looking at the original PaLM, one of Google's very powerful models, pathways to language models, large language models. It had used 4% of its input, I believe, had been Wikipedia in all of its different versions, language versions, but it was clearly playing an outsized effect on the quality of output. So understanding what data matters, and you could well imagine, for example, in some of the scientific cases, some of the problems are intractable without certain data being available.
And with that, I think we've also covered my next question, which is around specific data practices and how they've evolved, because we are dealing with these very powerful foundational models, which are used mostly in pre-trained form rather than perhaps the statistical methods that you had at the very beginning.
I think that's right. I'd just say, in addition to that, Eleanor, I think what we're seeing, as I say, is that smaller models, which aren't trained on nothing, on these very huge amounts of data, can still be very effective if they are tuned to particular tasks. So one of the things we're beginning to see is this emergence of particular skilled language models that have a specific capability in an area, and then the issue of how those are federated together. And this is giving rise to so-called agentic AI models, where you have a mixture, if you will, almost of experts collaborating together, each of which is running a different specialized model. Yeah.
Thank you for that. You've shown the data spectrum. We at the ODI work across the spectrum, but we're still very committed to open data because of the benefits it can have to ecosystems. So my next question is really, in this world where everyone seems to be scraping everything that is publicly available and potentially sources that shouldn't be made available, what is the role of genuine open data?
I think it becomes critical that particular institutions, whether that are governments, whether those are charities, whether there are research institutions, possibly universities, libraries, museums, they become really crucial parts of this ecosystem. We kind of saw that right from the outset of the open data work, which I regard as just unfinished business. This is an ongoing process. Certain data has been released, other data still could be. And I think those things, they become foundational elements. I regard open data, it's almost like the bottom of the pyramid in a certain sense. So the broader you can make that, the better. Of course, some data strains will be, for various reasons, more carefully shared. In some cases will be kept very specific to an organization or institution who wants to augment their model with that particular set of assets. But the broad base and the best argument you can make here is what generally happens in a lot of open science, where the databases in molecular biology and the databases in materials research are being made available and curated and managed, I would say, to as good a standard as we can, given our levels of understanding. That's always work in progress. So data is improved along the way, but in a way that's scalable and maintainable. Those assets become crucial for doing science in the age of AI. And that happens and applies, I would submit, in areas such as the law, where one would argue that certain of our judicial rulings or outcomes or legislation becomes an important feedstock, which works, of course, when it's broadly available and not captured within some much more narrow prescriptive publication regime, for example.
So I'm going to jump to some of the audience questions, and there's been actually a question and a comment about data infrastructure and FAIR and open science, and one participant rightfully says, well, progress with FAIR data and data reuse has been quite slow, or not
Patchy.
as fast as we would have expected. Is this a problem of incentives? And if yes, what could governments put in place to make this happen at larger scale, both for AI, but also more broadly?
Yeah, that's a great point. It is a lot of this is incentives. It's also about the workflow, the way in which people are rewarded and recognized. And I think for quite a long time, we've recognized, for example, in academic research, that until really quite recently, there really wasn't enough recognition and reward for those people who put the really hard work into maintaining data, stewarding it, making it available. I think that's beginning to change. I think we now have ways of citing and recognizing the data as an asset in its own right. There is even talk of, remuneration based on that, or career progression based on that. But I do think that's the key. I mean, is to work out what the incentive structures are for particular sectors and professions, and to recognize that this isn't something that takes care of itself. And I think in a very real sense, the data engineer, the hard yards on doing the data engineering properly, it is very much the Cinderella part of the whole exercise. And I think it's subterranean, it's under the radar very often, and it takes a real effort to bring it forward, and admire and promote it. When it's done well, you see real recognition for that. And again, I would point to examples like molecular biology, who've been working on organizing their protein databases for a long time, making them available, searchable, indexable, and so on. So there are lots of good examples out there, but it can take quite a lot to get the organizational permission, the professional incentive, and the individual expertise. A lot of this is just quite tedious to do. One of the hopes for AI is that one thing it might be very helpful at is doing some of the routine data engineering for us, rather than writing every line of code for us, but actually helping us equip data with metadata, for example.
And I like this Cinderella analogy. Typically, I talk about data work as being like plumbing, but this is a much better analogy to discuss these sort of challenges. I'm going to move us on to data governance. We had a number of questions on data governance. So one of them is really about the potential need to revisit the tools and processes we have for the governance of data sharing. And in particular, the question mentions data protection impact assessment. But in an age of generative AI, how does data sharing and the governance of data sharing change, in your opinion?
Yeah, and this is going to be being heavily contested right now, as we know. In the case of just general content, which people feel they have some IP claim over, we can see examples where platforms have done deals with those original content producers after the fact, perhaps rather than before. There are issues around other forms of what people feel is content appropriation. So the idea of what are stable and viable models, partly to ensure, just to come back, one of the keys that we've talked about is the idea that we need a good stock of human-generated content. The idea that we'll all be out of a job. I think one of the major areas is that the lived experience and the human activities that generate data become super important to keep the stock of data fresh, current, relevant. To your point about what do we need to do to modify our thinking here, again, sometimes this gets into the space where people are also concerned around privacy and the extent to which various forms of triangulation can happen with certain data, which in and of itself isn't disclosive, but when you put it all together, there is a lot of work now in every area, from public health through to various other work, and trying to think about privacy preserving machine learning, privacy preserving techniques. But the issue of doing the impact assessment, at least at the general level, to assure yourself that there aren't some particular issues with spillover of data sets, seems to me still pretty important. And we're beginning to see that right now, and not in the context of AI, but in the context of for example, genomic companies who go into administration, and then what happens? So I think we have lots of examples in the space of data management, aren't necessarily AI, that speak to the importance of these kind of discussions. Yeah.
There was also a related question, which was asking specifically about the differences. Say, if we're comparing generative AI or deep learning transformers with some of the some classical machine learning or statistical methods, what has changed in terms of data governance, if anything?
What has changed? I think a lot of things remain the same, because I think we're obliged to work through the issues of well, first of all, the quality of output. Are we convinced? What is it to have been confident that any intrinsic bias in the originating data has been accounted for, has been tuned out appropriately, or has been in some way accommodated? And I think that although it may be at much larger scale, even our current large language models suffer from the fact they have been constituted mainly out of a view of the world that originates out of the northern Western hemisphere, for example. And that isn't everything, for a start. So when we worry about particular demographics being represented, particular cultures being represented, particular areas that are more heavily patrolled in terms of the IP that's available, those are the kinds of issues that we worried about in an era of more traditional algorithmic, decision making. And so we do have frameworks there. I think what has changed is just the scale and just the sense of is this about putting genies back into bottles? Well, no, not really. It's about understanding where the fallibilities of these systems are, where the potential for exploitation, but also where the huge benefits are. Because what we have seen is huge potential for augmentation and amplification of the things we want these systems to do to help us solve the challenges around us. So if I think about a good example is the UN Sustainable Development Goals. I mean, there's an explicit group who worry about data for promoting sustainable development goals, whether it's elimination of hunger, clean water, the climate. And just by thinking about the challenges around how you organize data and how you deal with issues around privacy, around fair return, those models, those sectors give you a very good set of templates to think about the problem.
This also touches upon another question we were asked about bias in AI, and especially those initiatives that are looking at those frameworks and making a deliberate effort to collect better data that can help with that. So what you said about using AI for various data tasks has resonated with lots of people. So I'm going to get us into a few questions about that. So someone is asking whether one could potentially use data sets prepared for one sector or purpose for another task, right? So we're talking transfer learning and the like. Do you have any examples for that? What sort of thoughts do you have on the matter?
Well, I mean, in the case, of course, the case of the largest LLMs, or the large LLMs, is that their beauty is that they're, in a certain sense, they're general, and then you tune them to be specific. So there's a natural way in which what is happening in the tuning process is a specification to a particular domain. Whether or not a particular set of rules developed for training or indeed tuning allows you to transfer out, the evidence is there will be some transfer. That was always one of the real challenges for machine learning, the so-called problem of distribution shift. That if you change the nature of the task or the nature of the input distributions, you saw systems really struggling to transfer into other task achieving contexts. The great thing about absorbing the depth of knowledge that these systems have is that seems to be much less of a problem. If you take an area like the scientific discovery, where very specific data assets are used to train a model to solve a particular problem, whether it's protein folding or material discovery, there will be aspects of that problem-solving process that are reusable in some sense as insights in another domain. But there's also a lot of hard work to understand how you represent and how you put that data to work. So I think it depends a lot on the particular problems you have to handle. Yeah.
So I'm also wondering, given all the limitations of LLMs, whether we should trust them when it comes to creating metadata or publishing linked data.
Well, that's a good. I mean, that is true. I mean, there is this undeniable fact that even the very best models will still confabulate. They'll still produce a certain amount of hallucination. It may be down at the very low percentages now, but that still may be problematic. It may be the kind of key fact or key reference that ends up being crucial. But I mean, then the question is all about how you do the validation and verification of these systems. And we knew what that meant very precisely in the case of our theorem provers, for example, of our rule-based systems. We actually knew what it meant to be, the phrase was closed under deduction. What were the things you could provably prove in the system? And I think the challenge, of course, is that these systems have a different flavor to them, and as such, the engineering of these systems has produced remarkable developments, and we're now trying to tease out the science behind them and understand exactly what their modes of success and failure, strengths and weaknesses are, and how we can render them, for example, more scrutable, more transparent in a way. And that is, I think, something that even the founders of these modern fields would acknowledge. In fact, explicitly, Demis Hassabis has been talking exactly that. We need a science to emerge to account for these engineering artifacts we're now producing in the world. So plenty of research to be done for sure.
Absolutely, and plenty to understand also about what reproducibility and robust scientific methods mean in this context. So we have lots and lots of questions. So I'll have to curate, but there's a few questions that are asking about the potential of semantic technologies, knowledge representation, knowledge systems, metadata, and the likes in the AI. So well, I've merged a few questions into one.
We would say this, wouldn't we, perhaps, betraying our kind of intellectual journey through this. I think there's certainly the case you're seeing and you've seen in all of the very large systems used, other methods that more explicitly represent knowledge as causal networks, as structural knowledge that represents, for example, an ontology, a way of a taxonomy for a domain. These things have their place, not least in techniques such as retrieval augmented generation, which often can be used. You can use the knowledge graphs as an example, as a way of linking knowledge about how objects in a domain relate to one another, what the causal processes might be in a domain. So this allows you to enrich the style of problem solving. I think right down to the level of being able to link data. There's nothing in a sense that's oppositional to using these generative AI systems with semantic technologies. I think that one complements the other. I think if you go right back to an article that Tim Berners-Lee and Jim Hendler wrote in Scientific American in 2001. They imagined a world full of agents on the web that were threading data together, integrating and representing it back. That's kind of where we're headed in a sense. And the question will be, what advantage do you have if you've equipped data content on the web with metadata to be self-describing, to be findable and accessible? That simply makes the process of threading and integration more tractable. So I think you absolutely do have a space for these technologies. Yeah.
And I'm going to finish with another question that I have just merged from a number of comments we've received. It's about the role of personal data in all this. So we've spoken about medical applications of AI a lot. We haven't spoken about personal data specifically. The ODI has taken over recently the stewardship of the Solid open source project. So would you comment on this?
Yeah, I will. I think that's a great point. The extent to which you can gain insights using personal data, but secure in the sense that the data isn't leaving your stewardship, or that it is in some sense appropriately secured, or indeed in some cases encrypted. And people will always say, well, there are exploits to break these, you can never be sure or certain. But I think one of the attractive things about Solid is it re-decentralizes the web. So data assets aren't always absorbed into one database to feed the system. Now, the question about how you train these transformer models when your data is disaggregated or distributed across a whole set of places is again an area that's receiving research. Federated machine learning as a field exists, and people are working out how you can still get the benefits of building a model, a set of weights that represent the combined insights of all of those contributing data elements, but you've not put all the data elements in one place. And that kind of architecture is definitely something I think that will be important going forward. And just more generally, thinking about architectures in which there is more agency over for individuals or organizations or collectives to steward their data. You can almost think of, the ultimate scale, the ultimate data institution is a data set for yourself, which you, in some sense, is steward or created either by you or for you. And that's part of the vision of the social link data, the Solid protocol, we're excited about. The other thing finally to say is it brings back the individual. So in all the talk of AI and data, the age of generative data, we have to remember that this is about entangling people, humans, with these artificial systems. And that entanglement leads to all sorts of fundamental properties and behaviors that are social in nature, that demand the expertise of not just engineers and computer scientists, not just policy and data engineers, but actually of social scientists too. And ultimately, for all that content to be worth learning over, creatives, people in the humanities. So this is fundamentally about an interdisciplinary approach to the way we think about these challenges.
Thank you, Nigel. A very important point to finish on. And as always, thank you to our speakers and to everyone who's been participating in the discussions and questions. We weren't able to answer everything, but as always, we will provide written answers after the event. And just the pointer that if you want to stay in touch with work that we're doing at the ODI on topics like these, there is a newsletter that you can subscribe to. And I've also added here on the slide some pointers to some recent work we've been doing with Microsoft and King's College London, looking at that idea of using generative AI to do different types of data work, as well as an AI data taxonomy that unpacks some of the different species of data that are relevant in different parts of AI model development and deployment, which will require very specific solutions when it comes to governance and assurance. We are going to be back in December for a last webinar this year, and this is going to be a fireside chat with Professor Chris Johnson, who is the Chief Scientific Advisor in the Department of Science, Innovation and Technology. And we're going to talk about AI safety and the role of data in that. And you can already register. Some people have already registered for this, but you can already register with this QR code. And with that, thank you very much to everyone who's joined us this afternoon. Thank you, Nigel, and I'll see you all in December. Bye-bye.
Thank you.
Bye.